Last time we started to describe what is this BFV formulation of first class constraint system. So let me remind you what the definition is. So BFV system, it's a graded Poisson algebra. Which means it's a graded commutative algebra together with a Poisson bracket, which satisfies all the required conditions, just a graded version of the standard conditions for the Poisson bracket. And in addition, for the BFV system, in addition to this algebra, what we need to specify? We need to specify a special element called Biaresti charge. So omega sits in A. It has degree, which we agreed to denote by the term GOST. It has degree 1. And in addition, we have a Hamiltonian, H, which is also an element of A, but it has degree 0. And it's called Biaresti invariant Hamiltonian. It's an extension of the usual Hamiltonian. So that's the definition. And we say that if we are given with first-class constraint system, so there is a phase space M naught, then we have constraints T alpha, and we have Hamiltonian H naught. We discussed for quite some time these objects. Then we say, so if this is a first class system, then A omega H is called its BFV extension if I don't have place. Okay, I'll try to. If omega is equal to C alpha T alpha plus terms at least linear in P. I'll tell you what P is now. And H is H naught plus also O of P. And A itself, it's not going to be very nice. And A itself is an algebra of functions on the on our phase space M naught, tensored with polynomials in variables C alpha, and tensored with polynomials in variables P alpha. So, and index alpha is exactly the same like the one of our constraints, right? So what's the logic? So this is a general definition. It's just a graded Poisson algebra. We should think of it as an algebra of functions on a graded manifold, which is equipped with Biaresti charge omega. It's a distinguished element of this algebra. And of course here I forgot the most important part. The equations. It's not a good sign that you didn't correct me because we already discussed this. This is just a reminder. So this is the equation for omega. It's called master equation, and this is an equation for H. Compatibility for these two guys, right? So A is an algebra of functions on a certain extension of our phase space. Omega is a distinguished element which satisfies this strange equation. And H is also a fixed element, which is essentially our Hamiltonian, but adjusted a little bit to fit into this different formulation. And the adjustment is such that omega, the Poisson bracket of omega with H is 0. So this way we can define what is general BFV system. But eventually we are interested in concrete first-class constraint systems, and we say that if we are given with a first-class constraint system, then a BFV system is called its BFV extension if A has the following structure. So it's an algebra of our functions in our phase space coordinates, additional coordinates called Ghost variable C alpha, and additional coordinates called Ghost momenta pi alpha. And I should also recall you that we agreed that these guys C and P are canonically conjugated in Poisson bracket, right? So they are like coordinates and momenta. And degree of, let me also put it somewhere here. Well, I wanted to reserve space, well, here maybe. Gauss degree of C alpha is 1, and Gauss degree of P alpha is -1, and we agreed that the Poisson bracket of C alpha with P beta is delta alpha beta, right? So this is a very special situation, quite a specific BFV system, which contains as main ingredients our initial first-class constraint system. So we call such a BFV system a BFV extension. For the moment, we do not know if such a BFV extension exists, but in simple cases it obviously exists, because suppose that our constraints commute, and our constraints also commute with Hamiltonians, and we can just forget about these terms, right? And these equations are going to be satisfied because if we compute bracket of omega with itself, it will be C alpha C beta bracket of T alpha with T beta. If it is 0, then it is 0. Same here. If H naught commutes with T alpha, then without adding anything here, these equations are going to be satisfied. So you know that we know that in the simplest setup it exists, but in general it's a specific statement which we are going to consider. But for this we need some additional technology. So we want to give interpretation to our BFV system in terms without referring to these ingredients, what is inside, without referring to concrete constraints, constraint surface or whatever, just in terms of omega and H. For this we need some additional technology, and the first mathematical definition which we need, you will meet it many times in different courses, it's a definition of cohomology complex or cohomological complex. For us, it will be enough to consider complexes of vector spaces, but in general, this can be complexes of various objects, groups, algebras, whatever. So, by definition, this is a linear space graded. So it's a linear space which is a direct sum of a homogeneous components Vi. All of them are all VIs are linear spaces, and they are indexed by an integer number. In the standard assumption, which is not always satisfied in applications, then one has to be careful if it is not satisfied, if that only finite number of terms in this direct sum are non-vanishing. So first of all, it's such a graded space plus a set of linear maps, so delta I, which are maps from Vi to Vi plus 1. such that composition of delta I plus 1 with delta I is 0. And the mathematicians, they like to draw the following sequence. So start somewhere, then we have Vi, here we have delta I, Vi plus 1, here we have Vi plus 2, delta I plus 1, etc. So the assumption is that somewhere far away in the left and somewhere far away in the right, we get only zeros here, because these spaces are empty, right?
How long is it sequence?
I have not said that it is exact. No. Of course, it's everything is related, but this is just the definition of complex. That's a very basic object which you meet in many applications in mathematics and theoretical physics. I am sure many of you have already heard about this. Okay. So, given this, we can define something which is called cohomology. Usually we speak about cohomology groups, but in this case these groups are going to be just abelian groups, because our linear spaces are just groups. Okay, so cohomology. So given a complex, this is the definition of complex, cohomology is by definition, it's defined like this: Hi of our delta and our V is by definition kernel of delta I factorized over image of delta I minus 1. And maybe it's a good idea immediately to say that it's very convenient not to write this index I. So, and that's what always physicists do, and often mathematicians, but not always. So we define delta to be just a sum of delta i's, assuming that when delta I, because you see, delta I is defined as a map acting on Vi, but here I take a sum. It means that delta I, when it hits different V, whose I is with different I, it just acts trivially, so by 0, right? It gives 0. Then it's very convenient to write such a delta, because somehow you don't need to indicate. If you act on a homogeneous element, so of an element sitting in a particular V, it means that its respective component here acts, and the rest act by 0. That's a very simple convention. It's just about notation. There is nothing deep. And another remark about notation, that our agreement here is that our delta, which is called differential, it takes element of degree I, so element of Vi, to an element of degree I plus 1, right? But often it is also convenient to consider similar objects where differential goes other way around. Sometimes these are called homological complexes. That's why this co here. So co indicates that the differential rises the degree. If it is homological complex, then it decreases the degree by 1. But of course, if our agreement is that only finite number of elements are non-vanishing here, we can just change the sign of our degree to get homology into cohomology and other way around. In case if it's infinite amount, one has to be more careful. Anyway, for us, it's a question of notation. So historically, many objects are called homology and many objects are called cohomology, because in some canonical sense, they are dual and also the degree go like this. But for us, it's not so important. For us, it's just a degree, though we will meet both. But usually, we speak about just cohomology, not to complicate things. Okay, so what is cohomology? Cohomology is precisely the difference between what is in the kernel of delta and what is in the image of delta. So let me draw a picture here. So for instance, so this is our vi, for instance, for a certain I. Then we have a kernel here, right? So it's a subspace. So this is kernel of our delta. But inside kernel, there is an image, right? It's not a good picture. Let me draw it better. So this is our vi. Then we have a kernel. Let's say this is kernel. It's very schematic. We are talking about linear spaces, not manifolds, but still I draw it like this. So it's kernel delta in vi, and inside kernel there is a subspace image. Why it is a subspace? Because everything which is in the image automatically belongs to the kernel, because if we apply delta twice, we get 0. So if an element has a form delta on something, when we go with delta on him again, we get 0, right? So image is a subspace in kernel. Let me remind you that for us, for simplicity, we are only talking about linear spaces. And cohomology, by definition, is a quotient space of kernel by its subspace image, right? And a couple of more bits of terminology. So if delta f is 0, we say that f is a cocycle. All this emerged from studying topology. That's why names are a bit are very special. And so if f is equal to delta g, we say that f is a coboundary. Equivalent terminology, we say that f is closed. And in this case, we say that f is exact. And if we are talking about generic f, then we say that f, generic element of our complex, we say that f is a cochain. If you, well, you have lectures on differential geometry, then probably you know where it originates, these names originate from. Okay, and the standard example of a complex in geometry, example, is MD, where, let me better write it like this, omega of M and D, where M is a smooth manifold and D the Ram differential. Right, all conditions are satisfied. So differential forms on a smooth manifold, they can, it's a direct sum of forms of different degrees. So we have exactly this structure, plus the Ram differential takes forms of degree I to forms of degree I plus 1. So so we get a complex, and its cohomology is known as the Ram cohomology, right? Okay, but we are after slightly different type of complexes, but still it's a very basic standard example. Speaking about this, let me immediately introduce the notion of morphism for these objects. So if we have two complexes, V1 delta 1, V2 delta 2, we say that map V1 to V2, of course, because we are working with linear spaces, it is assumed that phi is a linear map, is called cochain map, or just morphism of complexes. Cochain map. If any ideas? By the way, it's quite easy to guess what it should look like.
Bermuda
Pardon?
Commutative squares from homogeneous space. I mean, like you have two strings and you have to have a map from pi to
Formula.
Delta
Form-
1 composed with phi equals phi composed with delta 2.
Yeah, something like this, exactly. So let's try. First of all, let's require the degree of phi. So it's, we can always shift it. What is important that it is fixed. So, and then we require the following. Indeed, we can first apply phi to get from here to here, and then we act with delta, right? Or we can first act with delta 1 and then apply phi. The result should be the same. That's the only natural condition we can write. So it means that a composition of phi with delta 1, right, this, or delta 1 with phi rather, is the same as acting first with phi and then applying delta 2. And you can also write the commutative diagram as Daria mentioned. Okay, and the last bit for the moment is we say that phi is quasi-isomorphism. Quasi-isomorphism if phi twiddle. We will check immediately that if phi is a morphism of complexes, then it induces a well-defined mapping cogomology. Because with this complex we can associate its cogomology, with this complex we can associate its cogomology, and phi induces the map from cogomology. Because cogomology are just equivalence classes of certain elements, right, which are in the kernel. So it's well defined. We will check it right now. And so if so phi is called quasi-isomorphism if phi twiddle is an isomorphism, which is a map from cogomology of delta 1 v1 to cogomology of, when I put this thing here, not a concrete number, it means that like all of them, direct sum, that's a standard convention. Delta 2 v2 if this map is isomorphism. If phi twiddle is isomorphism. That's a very important notion for gauge systems because quite often we meet indeed quasi-isomorphisms. As we are going to see, good language for gauge system is exactly the language of complexes or maybe even more general objects. And the same gauge system can be described by different means, by different complexes, but the physical content sits in cogomology and quasi-isomorphism corresponds to some kind of physical equivalence. That's the way it works. Okay, so let me leave it as an exercise to check, just to save time, let me leave it as an exercise to check that phi induces, this is exercise, induces a map of cohomology. It's just a consequence of definition, but one has to define this map in a natural way and make sure that it is well defined. It doesn't depend on the choice of representatives because you define it on representatives. Okay, fine. And now what all this has to do with this BFV system? So the statement is like this. Given BFV system, and remember that it is A, omega H, and A is, it is assumed that Poisson bracket is a part of definition of A because it's Poisson algebra. Given BFV system, A is a complex with differential, which is called BRST differential. BRST differential. Be very careful with this name because everything is related, but when you hear something like BRST operator, that's the most vague notion possible, it can mean many different, usually related, but still different things. So one has to be very careful, and terminology is not unique, unfortunately. So some people, maybe even this thing, sometimes it is called BRST differential by some people, by BRST operator. But I try to be consistent with terminology, and this is going to be BRST differential of this BFV system. BRST is again, well, it's a strange history. Many people contributed, and then first letters of their names were taken to, were employed for giving some kind of acronym. So this is Becky, Ruiz, Staray, and Tutin, who independently found the first instance of such an object. It was quite long ago, in 70s, in the context, of course, of gauge theories. Okay, so what is a differential? Traditionally, it is denoted by S, and it is nothing but a Hamiltonian vector field generated by omega. And again, it's a simple exercise. If it's not obvious to you, then I leave it as an exercise, that if we go twice, so this is a vector field, right? It's a Hamiltonian vector field because Poisson bracket is a first order differential operator. So if we substitute function here, we get a vector field, so first order differential operator. Then what we can do, we can apply it twice to a function. So if we apply it twice, so it is of course denoted like this, as S squared F equals to, of course, S F, and in fact it is 0 thanks to this. This is a simple exercise. That this equation here, master equation sometimes called, or it's very similar to what's called Maurer-Cartan equation in math. This equation, traditionally in this setup, it's called master equation because it's like main equation in this business which controls everything. Okay, so this is a simple thing to check, but for this you need Jacobi identity. But what is a bit less trivial, that in contrast to, so if we have a vector field, let's say Q vector field, so first order differential operator, we can check that Q squared, if you apply it to twice, is again a vector field if degree of this Q, well, I keep using this because we are in this setup, I keep calling the degree GOST of Q equals to 1. Well, in fact, any odd number would work. So if the vector field is odd, so it shifts the degree by 1, then surprisingly, if we act twice, normally we expect second order differential operator, right? But because something somewhere inside anti-commutes, if we square a vector field of degree 1, we get again a vector field. And another way to see it is that Q squared is just half of a commutator of Q with itself. It's a bit strange, right? But because we are talking about graded commutator, which has a sign factor, because Q has degree 1, this commutator contains plus, so there are two terms, QQ plus QQ. That's why half here and Q squared here. These are simple exercises, just algebra. You need to write down correctly these sign factors. But this is very important. And of course, you see some similarity between this equation and this equation, right? The master equation. because this master equation is again Poisson bracket. It's a graded Poisson bracket. It behaves essentially same way like a commutator, and this is an odd element. And it is this equation which makes sure that S squares to 0, because S is a Hamiltonian vector field with a Hamiltonian omega. Okay, so what we see that our algebra A, algebra of all functions on our extended phase space, extended because in addition to our initial phase space, we added some variables in our basic example. But of course, we can speak about generic. It's purely algebraic fact. We speak about generic BFV system, no matter where it comes from. If definition is fulfilled, then we know that A becomes a homological complex, and of course its cohomology is very important. And the physical interpretation, which we are going to check that it is indeed a correct physical interpretation, is that
what is the Gauss degree of a vector field? Because in supergeometry we are accustomed to the parity that is related on how the operator changes the parity, but here
yeah, it's exactly the same, but okay, that's a good question indeed, to avoid some confusions, because indeed these are slightly, it's almost the same, but there are there is a slight difference. So here we are speaking about, well, in general, A is a graded superalgebra. Well, with Poisson bracket, but that's additional. So there are two things. There is a degree, this Z degree, which I denote by GOST, right? And which, in this context, in this setup, the meaning of this degree, it tells me what is the role played by variables. So degree 0 means that we are talking about like our phase space coordinates, our something physical. Degree 1 means that we are talking about GOSTs. Degree -1 tells us that we speak about GOST momenta. But at the same time, if we have, for instance, in our physical system, if we have fermions present, we know that there are anti-commuting coordinates already here, right? Suppose we want to describe fermionic fields, like electron, or fermionic fields entering supersymmetric systems. Then it means that in Hamiltonian picture, in our phase space, some of the coordinates will be anti-commuting, but they are still physical. Their GOST degree is 0. But there is an additional degree. So here we have the Z degree. There is an additional Z2 degree, let's say Grassmann degree, which tells us what we are talking about, fermions or bosons. And the simplest setup, just to simplify the discussion a little bit, I prefer to say that we don't have in our initial phase space physical fermions. It's very easy to reinstate it. I think even in my notes I keep track of this additional degree and stay with just this Z degree. We still have anti-commuting variables, but their anti-commutativity is only because their GOST number is odd, not even, right? But if we had, in addition here, the genuine fermionic variables, we should have been more careful. Our real degree, which appears in, for instance, so let's say for a homogeneous function f, we should have really the total Grassmann degree. What does it mean? It means that fg equals to -1 to power ggf for two homogeneous functions. But you see, so this is total Grassmann degree. It tells us, so if we forget about this GOST degree, we have just total Grassmann degree, which tells us how our functions commute. So it means that we think of our A as just superalgebra, just like in your supergeometry course. In your supergeometry course, I suppose you don't discuss additional degrees. You just have one Z2 degree, which tells you how your functions commute. Like even functions commute, odd functions anti-commute, right? So that's it. But in this setup, in this concrete realization, if we don't have physical fermions, then our Grassmann degree is just induced by this degree. So Grassmann degree of f is just Gauss degree of f modulo 2. So it's, if we take z degree modulo 2, we get either 0 or 1, right? So we get z2. It is consistent. Our variables c, which are of degree 1, they anti-commute. Yes, yes. To be careful, we want this to be z Grassmann degree to be z2 degree. But in general, this total degree is not just Gauss degree, but it's Gauss degree plus genuine, let's say, fermionic degree. I don't know which name to give it. So you need to take care about 2 degrees, because anti-commutativity of variables could come from 2 different sources. One source is if they are, roughly speaking, ghosts or their associated momenta. But another source if in our M0 we have physical fermions. But we have too many structures already. That's why for a general exposition, I assume that we don't have physical fermions, not to carry all the time along this additional thing. But once we need it, and I suppose we will have such an example, it's easy to reinstate, because it's just important to remember that total degree should, in addition to Gauss, should also include this additional let's say fermionic degree. But what is a bit tricky is that, of course, constraints can be fermionic, but then their respective Gauss should have like also shifted by 1. Then the Gauss are bosonic. That's how it happens. And the BRST charge should have Gauss degree 1, but it should also have total Grassmann degree 1 to be an anti-commuting element, so that this equation makes sense. But for the moment, really, we have too many structures already. I suggest not to worry about this additional degree, which means that we are almost in the same setup like in your supergeometry course. The only thing, it's a little bit more refined. Our Z2 comes from a quotient of z of this by modulo 2, right? In fact, it's a bit simpler. Graded setup is simpler than super setup. Okay, fine. So this was like additional comment. So let's get back to our algebra. Now we have S derivation here, which is a differential, which can be considered as A to A. So it means that our A together with S is a complex. And we can say that our physical observables, let's call them, now for the moment to distinguish, BFV observables, inequivalent ones is just cohomology in degree 0 of S in A. So this, what does it mean? It means that these are equivalence classes of functions of degree 0 which are annihilated by S, right? So it means that SF equals 0, Gauss F equals 0, and F is equivalent to F plus S on whatever. So that's an equivalence relation, right? This is a definition of this cohomology, if you want. It's a space of equivalence classes of elements which are closed or which are cocycles, so which are killed by S, annihilated by S, of degree 0 because we put 0 here, and quotiented by coboundaries, which means that we implement equivalence relation. We consider elements of the form S acting on something as trivial, and we take a quotient with respect to this. That's another way of phrasing what cogomology is. Okay, and it's not difficult to check that evolution is well defined on this H naught. Evolution in which sense? We have this BRST invariant Hamiltonian, so in principle we can consider again it looks like a Hamiltonian system. So this Hamiltonian defines evolution, but what is non-trivial that this evolution preserves. It's like descends to cogomology. So it induces evolution of inequivalent physical observables, which are these elements of this cogomology group. It's easy to check. Let's try to check it. So what we want, if we have an element f, we define its evolution to be like, suppose nothing depends on time. So then we implement this dependence. We want to study evolution. We say that f dot is equal to fh, right, where h is now our BFV Hamiltonian, which is BRST invariant Hamiltonian. And if f is a representative of this cogomology, so suppose that in addition S f is 0, then let's compute S on f dot to make sure that this evolution does not destroy this property. So that it means that it defines an evolution in the cogomology group. So we can see the representative, so an element annihilated by S. Then we check if the speed of its evolution is annihilated by S, which means that we stay inside the cogomology. So let's compute it. Use this S acting on FH. Then we recall what is S. It is omega with F with H. And then we use Jacobi identity, and we see two terms, right? Omega hits bracket with omega, which means S hits F first, right? And the second term when it hits H. But in both cases, we get 0, right? Because bracket of omega with something is S acting there, and we just assume that F is unobservable, so S annihilates F, and also by assumption S annihilates H. This means that we get 0 here. So it means that if we start to evolve our observable using H as a Hamiltonian, it remains to be observable. And this means that we have an evolution, right? We can say that an evolution of our element of cogomology group of an equivalence class of F is just an equivalence class of, well, it's not a good idea, an equivalence class of f of t, evolution, how it depends on time, is an equivalence class of f of t, which is obtained just as a solution to this equation. So we get an evolution in our physical observable. So in principle, we can say that we have something like classical mechanics in cogomology. That's the idea. So this BFV system is some kind of extension of Hamiltonian mechanics, such that the usual Hamiltonian mechanics is recovered in the degree 0 cogomology of the BRST differential. And it turns out that such a representation, immediately it's not obvious why such a representation is useful, but it turns out that it is extremely useful in particular in quantization. If you want to quantize our constraint system, this approach helps us to like find a correct notion of what quantization is, etc. Okay, so these are our observables, this is our evolution, so we can give some kind of physical interpretation to our BFV system. But for the moment, it's not clear what this interpretation has to do with physical interpretation of the first-class constraint system, which we initially studied, right? So remember, to be more precise, if our BFV system is a BFV extension of a first-class constraint system, these constraints T alpha and Hamiltonian H naught and phase space M naught, then we want this interpretation to be consistent with the physical interpretation of our first-class constraint system, where inequivalent observables are, for instance, what? These are gauge invariant functions on the constraint surface, right? That's what we studied. But here it's some kind of cogomology, so we want to make sure that this is the same. But before this, we also need to show that actually given a generic first-class constraint system, we can construct a BFV system out of it such that it is its extension. For the moment, we don't know if such an extension exists, right? We know that it exists in very simple cases, where, for instance, all constraints T alpha commute, and where H naught also commutes with all the constraints. But in this case, we just write omega equal to Ct, H equal to H naught, and all seem to work, and it's not difficult to check that this is indeed the case, that these notions will coincide. But in general, it's a bit of work to prove the existence and also to give a constructive way how we can actually construct such an omega for a generic and H for a generic first-class constraint system. Before doing this, let me also demonstrate that it's very plausible that we are going to get the same physical interpretation.
Cosmology introduced them in order to get some topological invariance, right? Or what?
Not only. No, here it's not. Of course, it also contains information about topology, but not necessarily. Even if topology is completely trivial, this cogomology is non-trivial. In this sense, it's much more simple examples of cogomology theory than the ones originating from topology. Well, simple examples. In general, it can be as sophisticated, but you don't need to introduce non-trivial, topologically non-trivial manifolds in order to define non-trivial cogomology. Because this cogomology has to do with gauge invariance, not the topology. But but in fact the two things are closely related. So like if you do this for, roughly speaking, topological models, you get, without local degrees of freedom, you get cogomology similar to, analogous to ones which you get in topology. For instance, you can also you can also define, for instance, the RAM complex as BRST cogomology of certain constraint systems. But they are very special. They don't have locally they don't have physical observables. They're only like global observables. Okay, so let's suppose that we are given with a BFV system which is an extension of a given constraint system, so that our omega is C alpha T alpha plus dots. Dots means something depending on ghost momenta, and our H is H naught plus dots. Again, something proportional to ghost momenta. So let's analyze this condition that F is a cocycle. So we want to examine the notion of BFV observable. So we pick a function F and we require this. What does it mean? Don't forget that F has a degree 0, which means that F equals to F naught plus F1 plus etc., where as a degree, I use expansion in ghost momenta. Because it has ghost degree 0, it means that the number of, because where is the ghost degree can come from? It can come from either C or P. C brings +1 and pi brings -1. So if we have an object of degree 0, it means that the number of P equals the number of C. So if we expand in homogeneity in P, then the lowest degree term is just 0, which is ghost independent, right? So let me even write it like this. It is f0 of z, our phase space variables, plus f1, which looks like this. It's c alpha, f alpha beta of z, p beta plus more terms like this, right? And our omega is like this. So let's consider this condition. What it gives us. If we compute a Poisson bracket between such an omega and such an f, what do we get? We definitely get C alpha, T alpha F naught, right? Plus something more. So there can be a contribution if we compute Poisson bracket of this term with this, and this P hits C, so they are annihilated, we get something like this. C alpha, F alpha beta, T beta. And these are the only two terms which show up in linear order in C. So this must be 0. So, and let's look at this condition. Both are proportional to C, so we can erase C, right? By the way, I'm not sure, but it's not important anyway, that it's a right sign. Is it? No, it's not. It's minus. Okay, but it's not important anyway. So you see, you get this equation, but this is precisely the definition the definition that f naught is an observable, right? So it is something. It's a function on our phase space because f naught is a function of z only, whose Poisson bracket with constraints is proportional to constraints again, because our usual assumption is that our constraints are independent functions, so they can be taken as part of coordinate system. This simply means that it's equivalent to saying that bracket of T alpha with f naught vanishes on the constraint surface, and this exactly means that f naught is observable. So its restriction to constraint surface is gauge invariant. What about this is about this cocycle condition, but also there is an equivalence condition, right? We remember that f is equivalent to f plus sg. So this is what we can add. And f is of degree 0 in our case. So g should be in degree -1 because s brings degree 1. So let's write what is s acting on g of degree -1. What is this? It is s acting on g alpha of z p alpha. But next terms are going to be already like p, c something, right? And in fact, they are not so important for us. So let's see what it gives. And because we are only interested in we see that interesting part sits in ghost independent part of f. So we only want contributions from this SG which are ghost independent, and they can only arise from this term. So when S hits this, of course you get a term when S hits G, but this term is still proportional to P and we don't care about it. But the second one is when S hits P, and it looks like this: G alpha of Z, S acting on P alpha, and in fact, plus the rest is dots. The rest is always proportional to ghost, and this in turn, this is equal to what? bracket of omega, because S is a bracket with omega. So bracket of omega with P alpha. P alpha, to produce Ghost independent term, because of this, we can use the bracket between C and P, which is 1, right? So essentially, it amounts to G alpha of Z, T alpha plus Ghost dependent terms, which we don't care. So indeed, we see that this equivalence, which look natural from this homological algebra perspective, precisely reproduce for us the term that we, by adding the exact term or coboundary to our observable f, we add a term proportional to constraints. And this is exactly the equivalence which we were introducing when we were discussing first-class constraint systems. So it sounds very plausible that our interpretation is correct, but still, it's, for the moment, it's only morally, right? We see how it works, but what we really want to prove, first of all, that such omega and h exist for a given first-class constraint system, and second, that BFV observables are indeed isomorphic to Dirac observables, which we defined when we discussed constraint system without this language of ghosts. Once we make sure about this, we know that we just use we indeed have a different language, equivalent language to describe first-class constraint system, and then we are going to profit from the flexibility and power of this new description. Okay, so for this we need again a couple of ingredients which are very useful in different contexts, so it's not a waste of time to become acquainted with them. And the first ingredient is the so-called Koszul differential. So to see how it arrives in our setup, let's introduce the resolution degree. A resolution degree, which I denote by R_deg, and which is just homogeneity in pi alpha in our basic model. It's just a homogeneity degree in the expansion with respect to p. It's not a Gauss degree. It's a different degree. Of course, it is correlated with Gauss degree because these variables p also carry non-trivial, non-vanishing Gauss degree, but it's a different degree. And let's do the following. Let's expand our BRST differential S with respect to this degree. So S is equal to delta, which has degree -1. Let me, it's traditional S0 plus S1, etc. Such that our degree of delta is -1, and our degree of Si is I. Is it clear what does it mean, R degree of a operator? This is first order differential operators, all of them, right?
Can you clarify it?
Yeah, so we have this degree, right? It means that we can expand our, and we live in this big algebra A, right? So we can expand our A into homogeneous components with respect to this resolution degree. Now, it can't be negative because it's homogeneity in pi, right? So it's always non-negative. Into A, but let me put index in contrast to Gauss degree, let me put index up for A, right? What is AI? AI is it contains elements of the following form: f alpha 1 alpha I, depending on zeta our phase space variables and C alpha, because C now carries degree 0, it can enter everywhere, it doesn't change anything. And here P alpha 1, P alpha I, right? So AI consists of elements which are of homogeneity I in P, in variables P, right? That's clear. And for instance, if R degree of an operator delta is -1, it means that delta maps AI to AI minus 1, right? Because it like takes one of P's. It reduces the number of P's by 1. The question you could have asked me, why this expansion of our S, which is defined as a bracket with omega, starts with an element of degree -1, which plays a distinguished role clearly because it's like lowest resolution degree element. And this is just a simple combinatorics. Because you see, to obtain an element of degree -1 in P, it means that when it acts on something like this, well, of course, A is like collection of such elements. When it acts on something like this, it like subtracts 1P. It means it necessarily has a derivative with respect to P because it's a first order differential operator. To get rid of 1P, it should differentiate with respect to it, right? But it's a first order differential operator. So if it's differentiate with respect to P, it can't differentiate with anything with respect to anything else, right? And how can we get, for instance, here something of degree -2? We can't, because for this, to reduce the degree by 2, to lower the degree by 2, we need to get rid of 2 P's. But we can't, because by multiplying by something, we can only we can't lower the degree. We can only lower the degree by taking a derivative. So that's the only possibility. That's why it's the lowest degree term in the expansion of S. And this delta, in fact, in our simple case, it's easy to write it, because as I just mentioned, to have degree -1, you need to differentiate with respect to P. What is our omega? Our omega is C alpha T alpha. So to produce derivative with respect to P, our Poisson bracket should touch this C alpha to produce derivative with respect to P alpha. And actually that's the only term, because all other terms are proportional to P. And that's why they can't lower degree by 1. They can produce something of resolution degree 0 or higher, but not -1. So the only term, it's a simple exercise to check, is that the only such term is just produced by this term, where Poisson bracket touches C, which means that it is this, T alpha d over dp alpha. So it's very, in our simplest situation, it's very simple to write down explicitly this delta. It's not so easy to write these guys. First of all, we don't know omega even. We don't know the explicit expression of omega. We don't even know it exists. But suppose it exists, and by assumption it should start with something like this. We already know what delta is, right? Because delta can only come from the very first term, from this C alpha T alpha. And that's why it's easy to compute it. It is this one. And this is precisely what's called causal differential. It has its roots in commutative algebra. And we will see, at least the name comes from there. And we will see why and what it does. So let's study it a little bit, because it's a very useful object. It shows up quite often in different considerations. Not maybe exactly this, but it's slight generalization, but this is the simplest example. So So first of all, if we have an expansion like this, if we introduce any auxiliary degree, like this resolution degree, and expanded our differential as a series with respect to this additional degree, even without knowing any details of the internal structure of this differential, we know immediately that this lowest part is nilpotent. Is it obvious? So if you just write s squared equal to 0, then we expand, which is delta plus s naught plus s1, the same as 0. And then let's put together terms with respect to degree, homogeneous terms with respect to degree. So in degree minus 2, we will have this term, right? In degree 1, in degree 0, we will have the following term, s naught square half plus delta s1. And for instance, in degree, this is in degree 1, and minus 2, this is in degree, So this is minus 2. Then in degree minus 1, we have just delta commutator with, delta commutator with s naught, right? Which is just delta s naught plus s naught delta. They are all Grassmann odds. That's why commutator is always with plus sign, right? It's a graded commutator. Okay, this is degree minus 1. And in degree 0, we get what I wrote before, which is s naught squared plus delta with s1, right? But because these are homogeneous terms of homogeneity degree, different homogeneity degree in the resolution degree in this equation, they all should vanish. So in particular, it follows that this guy is 0, this guy is 0, and this guy is 0. They all should vanish, including the higher ones. So no matter what is the origin of the degree, what is the internal structure of this S, if the differential decomposes in such a form with respect to any degree, its lowest or highest, doesn't matter, the borderline piece in this degree must be nilpotent. So we get a new cohomology complex, in fact. So what we just checked, that delta squares to 0, and in this example it is obvious that this operator is squares to 0, right? Because if we apply it twice, pi variables are anti-commuting, while T alpha, just usual functions, they are commuting. So we get something symmetric matrix multiplied by antisymmetric matrix. Clear, right? Or shall I? So let's compute it. So suppose we act with delta and delta again on a certain function of z and p. What do we get? We do it twice, right? We hit once, so we get T alpha df over d pi alpha, and then we go again. It brings us T beta, and here we get like second derivative finally, d pi beta d pi alpha, right? That's the result. But pi, this or p, I always confuse them. I don't know what's the right name for this letter. These pi's, they are anti-commuting. So in alpha beta, this thing is anti-symmetric. But T alpha and T beta are ordinary functions on our phase space, they are commuting. So this expression is symmetric in alpha beta. So we have a multiplication of symmetric matrix by an anti-symmetric matrix, right? Contraction. And it is 0, of course, by symmetry reason. So the general statement is correct, right? We missed nothing. So delta squares to 0. And let's see what is. So it gives, we see this nice property, which means that our A has an additional structure of a homological complex with differential delta, right? So it means that our A together, if same linear space where we take another differential delta, is also a complex, homological complex. So of course, then the natural question is what is its cohomology? In fact, in this case, it's better to speak about homology because our delta is of resolution degree -1. So what is important here, maybe I should erase and put here R degree. So to consider this guy as a complex, we need to decompose A with respect to resolution degree, not as before when we decomposed A with respect to Gauss degree, but with respect to this additional degree called resolution degree, and then differential delta, it lowers the degree by 1. So we really have a homological complex. And what we are interested in is its homology. So let's first have a look in this example. What does it mean? So for instance, R degree 0. R degree of our element is 0. Then automatically delta F is 0 because resolution degree 0 means F doesn't depend on pi, right? But delta contains derivatives with respect to pi, so it's automatically like this, which means that the cycle condition is trivially satisfied. But the coboundary condition is non-trivial. So we know that F, if we want to compute cohomology, we need to take into account the equivalence relation that cocycle is equivalent to itself plus delta on something. And now this something should be of degree 1, right? Because delta has degree -1 and G has degree 1 in order to end up with something of degree 0. And what is the general form of this? General form of an element of degree 1 is something like this, right? It's just homogeneous element which is linear in P. So let's continue. So what it gives us F plus G alpha T alpha. So you see that equivalence relation, so the image of our differential allows us to add elements proportional to constraints in degree 0. So any element of degree 0 is a cocycle, which just by degree reasoning, there can be no pi, but still there are, so everything is a cocycle, but still among these all cocycles, there are elements belonging to the image, so the coboundaries, and they have the following form. They are functions on our phase space proportional to the constraint. So what is cohomology? It's a quotient of all functions on phase space, modular, but it's a quotient of all algebras of all functions on our phase space by those which are proportional to constraints. So what is this? This is precisely the implicit definition of algebra of functions on the constraint surface, right? So H naught of delta and here we are in A. This is precisely our algebra of functions on constraint surface, but the only thing we forgot is A also contains C variables, but C variables are not affected by this differential. It doesn't involve C variables, so they just remain a tensor factor, tensored with polynomials in C. Right? So it's very easy to compute cohomology of this differential in degree 0, because cocycle condition is trivially satisfied. Comboundary condition allows us to add something proportional to constraints. under standard regularity assumptions, which we assume that T alpha independent functions, it means that constrained surface is a good surface. This quotient is just algebra of functions on our constrained surface, and we keep track of this factor just for consistency, not to introduce different algebras, because variables C are completely passive in these considerations. They become important when we start to consider these new differentials sitting there, but for delta does not differentiate with respect to C, so it doesn't see it. You can always reinstate this C dependence. Is it clear? Questions? Here we are, very slow. We are very slow. Okay. Fine. So this was very simple in this computation of cogomology, but what is more difficult is to compute this cogomology in positive degree. So the negative degrees are not present, so there is nothing to compute. So the general statement is like this, that hi of delta A equals to this for I equals 0 and 0 for I greater than 0. But the very important condition is that T alpha independent functions. The idea of the proof and exercise give a proof, give a local proof, exercise, size, local proof. Local in the sense that instead of considering all manifold M, we just consider one coordinate neighborhood. So suppose that our manifold M0 is just Euclidean space. In fact, it also holds true globally, but this is like second part of the exercise, and it requires using partition of unity. At least the proof I know. It's a bit more difficult, but if you want to exercise, you can exercise. But locally, it's very simple, and the idea is to use T as part of coordinate system, because we assumed T to be independent, so we can use them as part of coordinate system, and then this differential becomes a linear differential operator, first order, right? It looks exactly like the Ram differential. It just tells you that you get rid of one P and substitute with T, right? And we know that such operators, for them, it's easy to prove that cogomology is given by constants only in 0 degree. But in 0 degree, that's why. But constants means independent of T and P, which means functions on sigma. But in positive degree, they are empty. It's analog of Poincare lemma. The only thing that it's like other way around. The Ram differential in Poincare lemma is something anti-commuting times derivative with respect to coordinate. Here it's other way around. It's like dual. It's something commuting times derivative with respect to something anti-commuting, but the idea is exactly the same, and the proof is exactly the same, like the proof of this, let's say, supergeometrical proof of Poincare lemma. So it's an exercise, give a proof. Another piece of terminology, when we have, when it happens that we have a complex such that its cogomology is concentrated in one degree only and empty in other degrees, we say that this complex gives the resolution of its cogomology. So you see what happened. Our cogomology is an algebra of functions on a surface. Forget about this C, doesn't matter. This C also, let's consider it as a part of sigma. So we have an algebra of functions on the surface. But if you want to find such a complex, such a homological complex which is simpler than this algebra, but is such that this algebra appears in cogomology of a certain differential. This can be very useful because, remember, our phase space is usually quite good, right? It's like some phase space coordinates, fields, something, but constrained surface can be quite tricky. And it's not very nice to work. Like, if everything is finite dimensional and everything is regular, it's easy for us to write this, but it's not so easy to really work with this object because this means like algebra on a tricky surface, which can be non-trivial, where we don't have a good coordinate system. In field theory, there are issues with locality, so we prefer not to work with it. But this Koszul differential offers us a good technical tool to work with such objects. It tells us, look, don't consider it. Instead, consider our algebra of functions on our extended phase space. Just introduce these p variables and introduce a simple differential, which is also completely explicit. And then the general statement is that you recover what you want in cogomology. That's a very deep idea which works in many different places in math and physics. Physics, of course, I would rather say mathematical physics. But it's indeed a deep story, because it's a way. So if you have something not very nice, a modern mathematician immediately would tell you, no, I'm not going to consider this object. I'm going to consider its resolution and work with it. And that's why this approach is useful in quantization. Because what is quantization? We are going to somehow deform these structures. We don't know how to deform them in terms of this sigma, because it's very difficult. It's something in field theory, it's an ugly, non-local, non-linear, whatever object. But A is still good, and delta is still good. So we are going to deform the resolution, the complex itself. This is the philosophy. It's not very concrete, but you will see how we are going to use it to define what quantum mechanics in this terms is. Okay. So, and this complex is called Koszul complex. It's a very simple and specific example. If you talk to mathematicians, they would probably disagree with you, because originally I think it was introduced in the context of commutative algebra. If you have an ideal generated by certain elements, how to describe quotient. And to describe quotient, you consider some kind of differential. Of course, their terms were different. Some kind of differential of this type. So you describe the quotient as a cogomology. You do a resolution of the quotient. Essentially, we do the same, except that our considerations are more geometrical. We want to resolve the algebra of functions on the surface, which is, of course, a quotient of commutative algebra by an ideal generated by certain elements, and these certain elements are our constraints. Of course, the story becomes much more interesting when T alpha are not independent functions, but this is also this can also be handled. Okay, I have something like 10 minutes, so let's get further. So we know what our Koszul differential is, and we are going to give an example, and a useful example in this setup, of morphism of complexes. So we introduce a new complex. So what we are going to do, we are going to take, let's call it on shell. On shell, because it's like on constraints are solved. On shell, BRST complex. So this is kind of definition. Of course, it's not a genuine mathematical exposition, but still, let me try to fix some terminology. So what is on shell complex? It's, as a linear space, it's a cogomology of delta. Yeah, better like this, because it has like resolution degree and Gauss degree. And I take just cogomology in whatever degrees. So I computed this cogomology, and in fact, there is a differential sitting there. And this is on shell BRST complex. But I need to, so I explained what it is as a linear space. In fact, under regularity assumptions, it is just this, because we know the cogomology. We just computed it. And what is gamma? So gamma is defined like this. Gamma acting on an equivalence class of delta cohomology is just, by definition, is just S naught acting on F. Yeah, let's put F. So any F we can decompose into resolution degree. So there is a well-defined map. To each F, we can associate an element of resolution degree 0, the lowest resolution degree term in the expansion in P. So this is P independent. This is like linear, etc. So we know anyway that cohomology shows up only in degree 0. So we define a new differential here. We say that gamma act on an equivalence class by the following rule. You take a representative, you pick a pi-independent piece from the representative, and you act with S naught on this piece. And then you take an equivalence class. So after such a definition, what we need to check? Yes, so correctness. It's called correctness. Correctness. And another, if it is well defined, yeah, we get differential gamma. But what we are not sure about is that gamma squares to 0. That's we also need to check. So with correctness, it's, well, everything is simple actually. So let's check correctness. So suppose we go with gamma on F plus delta G. We pick a different representative. We added a coboundary here. So by definition, it is nothing but S naught acting on this, right? And then equivalence class taken. But then, do you remember when I analyzed the condition S squared to 0 expanded in resolution degree? So first, in the degree -2, it gives delta is nilpotent, squares to 0. And then in degree 1, you get this, that delta commutes with S naught. So it means that what you get here is the first term, which is the same. And then with a minus, you can take S naught through delta, minus delta S naught G. But this is delta exact, so it's trivial in cohomology, and equivalence class kills it. So it is S naught F. So it's correct, right? Gamma is well defined. It's a perfect operator acting on here in cohomology of our Koszul differential. And then we need to check that gamma squares to 0. So let's go twice with gamma on the equivalence class. What do we get? We get S naught squared acting on F, but S naught squared is not 0. And now we look in here. That's what we hit. This is a piece in the expansion of this nilpotency condition with respect to resolution degree, and that's what we get in degree 1, right? Because here it's in degree 0, sorry. So this is -2, -1, this is 0, right? Delta S1 and S naught squared. You see what it says? It says that the square of S naught is itself like commutator of delta with something. So it's already a bit suspicious that it's not far from being 0, because it's like delta acting on something in the sense of a joint action, of course, for the moment, because we are talking about operators. So let's use this identity here. So we can exchange with a minus sign. We can replace S naught squared with this guy. So we get commutator, but let me do it delta S1. Let me do it explicitly. Delta S1F plus S1 delta F. Sorry, not here. I should put not here everywhere. right? But delta on F naught is 0 because it's a cycle of delta, and this is exact. You see, because it is delta on something, so it is 0. So you see that, so gamma, that's why I use different notation. Gamma is not S naught. S naught is not nilpotent, it's not a differential, but S naught induces a differential in cogomology because S naught is nilpotent up to something like commutator with delta. And this something, which is commutator with delta, becomes 0 in cogomology because it contains two pieces. It contains delta S1 and S1 delta. S1 delta kills any cocycle, and delta S1 is trivial because it is in the image of delta. So it becomes, you get a new complex. So what we showed that we constructed a new complex, right? And this is called on-shell BRST complex. On-shell because it is now its natural realization. Of course, you can realize it differently, but we know that this cogomology is the only non-trivial piece in this age in usual situation where regularity is assumed as we compute is just algebra of functions on the constrained surface times costs. So, and this is sometimes called shell, right? Like mass shell, and actually it is almost mass shell in applications. That's why it is on shell, because some like constraints are imposed. And this is a new complex which is a bit simpler because now we only have variables of degree 0 here and degree 1 here. We don't have negative. That's why we can't get this infinite, well, in this case anyway, finite, but this long series expansion in GOST. So if we have an element of degree 0, it's just GOST independent. If we have element of degree 1, it is just linear in C. And the statement, which I try to prove it, but we will discuss its proof because it's not completely elementary, but it's a bit of an exercise, nothing special. So the statement is that AS is quasi-isomorphic to this H delta A gamma. So degree is the same, it's called degree. So the map is very simple. It just takes if you have a cocycle of S, you take its pi independent piece and take its equivalent class because its equivalent class in cogomology of delta. So its equivalence class modulo adding functions proportional to t, and this gives you a map from here to here. It's easy to check so that this map is a morphism of complexes, so it's a cochain map. So let me nevertheless write it. So phi from A to H, let me for simplicity say not here, because anyway cogomology is concentrated in resolution degree 0, H0 delta A. So phi maps phi of F is by definition an equivalence class of F naught, where F naught is a p-independent piece, and equivalence class means its equivalence class by the equivalence relation of adding functions proportional to constraints. So it's precisely adding the delta exact terms. So this is a map. And phi is a morphism of complexes because by definition we defined it like this. Actually, we already proved it. That phi acting on, for instance, S F, right, what it is. It is phi s naught f, delta f plus s naught f plus etc. Right? I just explicitly expanded s. Of course, this term is delta exact, so it doesn't play a role. And this term, again, only if 0 here contributes. So it is phi, and all other terms sit in different degrees, so they can't contribute. So we get here S naught, F naught, and this is by definition gamma on F, right? Yeah, like this. Even of F naught, doesn't matter. So it's a morphism of complexes, so we checked this explicitly, but the exercise proof quasi-isomorphism. It's a bit of work, but who wants to play a bit with cohomology theory? That's a good and simple exercise. And the final remark, and in fact there is a very simple geometrical realization of this quasi-isomorphism, because so we have our space M, which is extended phase space, where we have coordinates z, let's say A, C alpha, P alpha, right? These are our phase space coordinates. And there we have our S, it's a vector field. S, vector field on M, right? And what is this H0 delta A? You remember that this is C infinity of sigma tensored with functions in ghosts. In fact, this is nothing but C infinity on, let's say, sigma, let's call it sigma x, so it's our sigma with addition extended by coordinate C alpha, right? Because that's exactly what we are talking about. Just in geometrical terms, it's an algebra of functions on our sigma extended by anti-commuting variable sigma C alpha. And this is like extended constraint surface, but this sigma x is in fact a submanifold in M, singled out by P alpha equals 0 and T alpha equals 0, right? That's exactly what we are doing. I'm saying almost nothing. So sigma is where we put T to 0, but we also have C and P variables, and here we don't P variables, we also set them to 0. So we can think of this extended sigma, where these guys are functions on, as a surface embedded into M. And a simple exercise is to check that S is tangent to sigma x. This is very simple. If we go with S on P, we get actually T plus something ghost dependent, but this ghost dependent vanish when P equals 0. And if we go with S on T, we again get, well, that's an exercise, check it. So you see the picture is very nice, geometrical. If we are allowed to think about these spaces as, but it's still useful to imagine something geometrical, though it's very difficult to imagine directions which are anti-commuting, but still, so we have this M, and we have this sigma x, like same picture. But now it's extended phase space, and this is extended constrained surface, and there is this vector field S, and it is tangent. Do you remember? It's like when we thought about constrained system in terms of constraints, these vector fields generating gauge transformations, they were tangent to constrained surface. Now they are all sitting inside this S, in fact, if you work components a little bit. And it's enough just to make sure that S is tangent to this surface. And the restriction to this surface is precisely this quasi-isomorphism stated in this proposition. So we just restrict this algebra of functions to a submanifold because that's how we can realize this cogomology. And gamma is just a restriction of S to this surface. And in terms of coordinates, you can write that gamma, because it is of degree 1, must have the following structure. It's C alpha, like T alpha restricted to the surface, plus possibly C term of this structure. And that's it. So gamma is very simple because we don't have negative degree variables. Omega can have many, many terms in the expansion, but gamma can have only 2 because it must be of degree 1 in C. And so it either has term proportional to C and which takes derivatives with respect to phase space coordinates, or quadratic in C plus derivatives in C. There can't be high order terms in C. So it's a closed expression. It is important. It gives some conditions between these two. And in fact, this is an object. This is a geometrical object which is called Lie algebroid by mathematicians. It's phrased in different language, but once you have such an object, it means implicitly you have a certain fiber bundle over sigma, where C alpha like coordinates on the fibers, and such a differential, and this is called anchor, and this is called whatever, bracket of sections. So it's also a known object. So I have to stop here. Thank you.